In this video, I'm going to go over the use of some of these little logic boards that I've supplied with your lab set. The first ones that we're going to look at are the dip switch board and the bar LED board. So starting with the dip switch board, first of all, you'll notice the numbering is a little funky on here. On the switch it goes from 1 to 8, left to right, but on the text on the bottom it's going from 0 to 7. So what I really want you to reference, and that also matches the 0 to 7 on the top here, and I want you to kind of keep track of those numbers. You could ignore the 1 through 8, because in binary numbers, the rightmost bit is considered the least significant, or the smallest value, and the leftmost bit is the most significant value. So that's typically how I'll refer to it. So these dip switches have pull-up resistors, or rather pull-down resistors, so that if you flip it to the on position like that, in this case, this is output 7, that would put an output high on 7, and if it's switched off, that would be a low. Because the resistor's built in, you don't need to worry about the logic level on that, or that it would be floating as an output. Now, the bar LED is positive true, so that if an LED lights up, it means it's seeing 5 volts. Now, unfortunately on this, I left off the pull down resistors, and so what happens then is if I touch this, you'll see that I can actually turn on the inputs just by touching it with my finger. And this is the whole issue I've been talking about with using pull-up or pull-down resistors. The input currents to these pins are so high, the amount of current needed to switch it is so high that a floating input can come on as a 1. Or it might be a 0. It's unpredictable. However, if we, for example, connect our output here, 1, to our input here, 1, okay, and flip it on and off, you'll notice that it turns on a bunch of them. And the reason why is that the actual leakage current between the inputs on the device are so small that even that one input will turn the other ones on. So most of the time we'll be wiring all these inputs to the output of an IC, so we don't need to worry about this. But let me just show you. If I went ahead and wired up a bunch of these, I'll pause it so you don't have to watch this. Okay, so now I've wired up all the outputs. A couple things to note here. First of all, these are grouped in kind of nibbles or 4 bits. So you got to be careful. Don't just wire them up from 0 to 7 in a row. You'll notice that these are split into 2 sets. So there's a gap between them. So just kind of be forewarned about that. And so now, if I turn on these individual switches, everything works as expected. I can turn on inputs and outputs. The whole point of this is to save you from having to wire in 8 LEDs and 8 switches whenever you need to make these kind of connections. A couple other things here. Make sure that when you plug these in, the ground pins are plugged into the blue strip on the bottom, which is going to your ground wire. Please do me a favor. Before you power these, before you plug them in, check and make sure that your voltages are at 5 volts. If your power supply fails and it puts out 12 volts, you'll blow out all these boards, and I don't have a lot of spares. So just please check that. Also, before you power up your power supply, take a meter across your red and black leads and check out resistance and make sure there isn't a short circuit there where you'd have a low resistance. So the reason I'm mentioning the on this board is if you go all the way to the other end of the board, you'll notice that the positive is on the top, okay? And if you plugged in your board backwards like that, it would short it out. It would take the power to the wrong pins. So just be careful with that. Okay, so that's the LED output board. I call it the bar LED. This is called the bar graph LED. By the way, the last 2 or first 2, however you want to look at it, those are not connected to anything. So don't expect to see those turn on. If the little LEDs aren't on, you'll know that you don't have power to it. So for example, if I pull the power pin, you'll see those LEDs turn off. So use that to kind of diagnose your circuits also. Okay, so let's take a look at a couple of the other ones then. Okay, the third board that we're looking at is the pulse generator board. And this is basically a 555 timer circuit. Same way connecting power and ground. And it has 2 things, or a few controls on here. It has a switch for turning the signal off. When you do that, it actually just runs high there. And it has two potentiometers for fine control and coarse control. It also has a jumper that selects a low frequency and a high frequency band. So first of all, let's just go ahead and hook this up. So for example, if we wanted to drive an LED with this, we could connect a resistor there and the LED to ground. Whoops. Oh, I was off. There we go. There we go. And you'll notice that it's alternating. So this LED is coming on when the signal is low. But that's what that little kind of square wave signal represents there. So for fine control, we can kind of control the speed in a more fine manner if we're trying to get it to a certain frequency. The coarse allows you to go through a really wide range. Now, unfortunately, the way I designed this board, I had the potentiometer leads were flipped. And so it's when you actually go clockwise, it goes faster, but the knob kind of looks like it's turning the wrong way. Now, so the slowest rate you can go is on the order of probably maybe 5 or 6 seconds, something like that, a really slow frequency. If we move this jumper, this bridging jumper here to the H side, now we can actually adjust it, but it's a pretty high frequency. And so it's going to probably be hard for you to see it actually like flickering on or off. But if you wanted to have something that's a higher frequency, you could flip that over to that side. For the most part, the low frequency will probably be fine. But we'll play around with that a little bit later as we get into some more of the circuits. I think for this lab, we're going to be doing something on the order of 100 hertz, which will be pretty fast. Okay, so that's the oscillator board. Okay, this next board is the switch debouncer board. And basically what this is 2 push-button switches. Your colors will probably be different than what we see here. But it's a debouncer, which means that when you press this button, it'll put out a pulse, but it's a very clean pulse. You won't get a lot of extra switch bounce. And we'll be using that later a little bit with the switching circuits. So what's important here is you've got 2 outputs, output 1 and output 2. Again, make sure that you're lined up with the proper pins there. There's a space between those. This actually uses a little surface mount 7414, which is an inverter with what's called a Schmitt trigger, and then some capacitors to stretch out that signal. So that'll be convenient when we're trying to load a value into a register, but we don't want to have 50 pulses go into it. Power, same way, ground and 5 volts on the rails there. Okay, the last board is the 7-segment LED display board, and the color of your LED display might be different than what you see here. What this board has is a 4-bit input that is decoded from binary into decimal value on the 7-segment display. And there are also a load, LD, a phase, pH, and a blank input. So the load I've actually got going over to this push button switch. The phase I've got going to output 6, and the blanking I go to 7. So first of all, if the blanking is high, it turns off the LED display. And we'll actually be using that later on. But one of the first things to check, if you've got power on your board and your display isn't working, you might want to check and make sure that the blanking is set. The phase, I think for your boards, is almost always going to be a high. And what that does is basically allows you to invert the outputs of the 7 segments. This is useful if you have, like, for example, a common cathode display instead of common anode, where all the inputs are flipped. And it's also used for LCD displays. But I think for all your boards, you're probably going to have that up. And then the third input, which is the load, basically will take a pulse coming in, and whatever data that we're setting on these 4 pins would be loaded into the LED display. So if, for example, we have a 1 flipped up, it stays 0 because it isn't loaded yet, but if we press it, it loads the value in there. So for example, if we had 1001, that's equivalent to 9. I press it and it loads 9. But again, you'll notice if I change it, it doesn't change until I actually hit the load button again. So that pulse loads whatever data is coming in from these 4 bits into these 4 inputs here. If this is kept constantly, let's see, if we take this low, oh, maybe it's high. Yeah. If we take that load input high, it will just, it's just taking the data directly from the inputs to the display. But there are times where it's convenient to actually load the data. Now, one other thing I want to show you really quick here. If we select a value greater than 9, obviously you can't display a 10 on an LED display. I believe what happens is, yeah, it blanks out. So any value larger than 9, anything from 10 and above will display as a 0. But as soon as you go back to a regular number, you'll see a 4-bit value that's a BCD value. It will display on the LED display. Okay, so these boards, we're going to be using them for the next couple of weeks. Hopefully they'll save you a lot of wiring, but please, please, please be careful with them. Try not to damage them. The dip switch and the LED board are pretty durable, but again, they could be damaged too if the voltage is incorrect on them. Okay, and this will help you out in your labs in this week.